Jnanam paramam dhyayam. Knowledge is supreme.
How to get row echelon form, how to get a reduced row echelon form, right? And we said that these row operations can be achieved by elementary matrices. Pick up the suitable order elementary matrix and pre-multiply A with that matrix, you will get that operation. Okay, right. So we can write another theorem that let us specialize this to a square matrix. Suppose you have got a square matrix n cross n, okay, and you look at its reduced row echelon form. What are the possibilities? Number of columns is equal to number of rows. So one possibility is the number of pivots that R is equal to n, right? That means every column will have a pivot, right? Two possibilities for a n cross n matrix. If you look at the reduced row echelon form of that matrix, then what is the possibility? The number of pivots is equal to number of rows equal to number of columns. That means each row and each column will have a pivot, right? And every other entry in that pivot column is 0. So what does that matrix look like? That is precisely the identity matrix. So one possibility for a square matrix, when it is reduced to row echelon form, reduced row echelon form, when it is transformed to reduced row echelon form, that form is identity matrix, that is one. Or what is the possibility? Number of pivots is less than n, right? One was equal to n, other is less than n. That means what? That means at least one row at the bottom must be 0. It cannot be more than, it cannot be equal to n, it can be at the most n minus 1. So there are only n minus 1 pivots. That means at least one bottom row should be equal to 0, right? So there are two possibilities for a square matrix in the reduced row echelon form. Either the reduced row echelon form is identity, or at least it will have one row at the bottom which is all 0, right? Okay. The proof is rather obvious, because once we do those operations, right, it only depends on the number of. So if the number of pivots is that p less than n, then n minus p rows at the bottom will be all 0, right? And you can see that on that portion of the matrix where pivots are coming, that will be identity. That portion will be identity matrix, okay, right? P cross p on the left side will be identity. So let us now, how is that useful? We are going to give an application of it. So let us start defining what is called the invertibility of a matrix. You all must be knowing that already. Where invertibility is defined only for square matrices. It is something to do with multiplication. Like for numbers, every number which is non-zero, right, say alpha, has a multiplicative inverse 1 over alpha. Product gives you 1. Right. So in matrices, for addition we already have identity, right? If m cross n matrix A, you add a matrix m cross n which is all zeros, that do not change the matrix, right? So that is additive identity for the matrices of order m cross n. When you want to multiply, so you can multiply on the left as well as on the right. So for example, for number 1 over alpha into alpha is same as alpha into 1 over alpha, multiplication is commutative, but matrix multiplication is not commutative. A into b need not be equal to b into a. First of all, a into b may be defined and b into a may not be defined for rectangular matrices. Even if it is defined, they may not be equal, right? So to say that something like inverse exists, we have to put a condition that A is a square matrix of order, any order. We say A is invertible if there is a matrix B, say that A into B and B into A both are defined. They will be defined if B is also of the same order as the matrix A, right, are defined and equal to identity matrix. A into B multiplied, that means multiplying A on the right side by B or multiplying A on the left side by B, both products should be equal and equal to identity matrix. In that case, we say the matrix, this matrix A is invertible, right, and this matrix B we call as inverse of A. The B is called A inverse, I am saying A inverse, but one can show very easily that if one such exists, it has to be only, it is unique. That means, if there exists a matrix B with this property, right, then there is only one, there cannot be some other matrix also. So, if A inverse exists, it is unique. So, we call it the inverse of the matrix. So, this I will leave it for you to verify, right, that it is unique. That means, if A into B is equal to B into A also equal to A into C and C into A equal to identity, then B must be equal to C. Next, if A and B are invertible, so these are properties of invertible matrices. If A and B are invertible matrices and you are able to multiply them, right, that means what? They are of the same order. Then A into B is also invertible. Product of invertible matrices is again invertible, and the inverse of the product is product of the inverses. So, A B inverse is same as order is interchange B inverse A inverse. So, that helps you to compute inverses of products for invertible matrices. So, this also you should verify. Now, let us look at elementary matrices, these three elementary matrices. What were the elementary matrices? We took an identity matrix, right. For example, we interchange ith row with the jth row, we got an elementary matrix. Is that matrix invertible, the new one that you get? Is that invertible? Intuitively it should be, because I can reverse that operation, right. And what is that operation? Multiplying on the left by some matrix, right. So, if I invert that, if I added, I will interchange, I can again interchange, what I will get back? Identity, right. So, elementary matrices, they are all reversible operations, right. Interchanging ith with j is same as reverse j with I, adding one jth row to I, right, subtracting back, okay, multiplying by a scalar non-zero, that is why we said non-zero. There are two reasons: one, in the equations that equation may become 0, data may be lost. Another thing now comes here, if you are multiplying a row by a non-zero scalar to get that elementary matrix, then you can multiply by 1 over of that, you will get back the identity matrix, right. So, all these elementary, three elementary matrices, three types of elementary matrices are invertible matrices, they are special matrices, they are all invertible, right. So, for example, we have written here that if you take Ejk, and what is the inverse of that, right. So, inverse of that is it should be Kj here, there is a typo, it should be Kj, interchange again Kj. So, for example, Ej lambda, that means you are multiplying jth row by lambda. So, divide jth row by lambda, that is the inverse. So, inverse operations. So, all elementary matrices are invertible matrices, and keep in mind what is our definition of invertibility. It says there is a matrix B, so that A into B is same as B into A is equal to identity. Later on we will see other definitions of invertibility also, okay, but we are starting with a definition that like numbers, right, for every non-zero number alpha there is inverse 1 over alpha, multiply alpha times 1 over alpha is equal to 1 over alpha times alpha equal to 1. Similarly, so matrix is, if given a matrix A, if there is a matrix B, say that AB is equal to BA is identity, then we say A is invertible and B is called the inverse of A, it is unique. Clear? Okay. So, now let us look at now start relating invertibility with elementary matrices. So, theorem says a square matrix A is invertible if and only if, is a necessary and sufficient condition, says it is a product of elementary matrices. If a matrix can be split as a product of elementary matrices, that obviously each elementary matrix is invertible, right. Product of invertible is invertible. So, one way is obvious, if a matrix is a product of invertible matrices, it is invertible, that is obvious, right, because if a matrix A is product of invertible, right, each invertible is if A is a product of elementary matrices, each elementary matrix is invertible, product of invertible is invertible. So, A is invertible. So, one way is obvious. So, let us look at that proof. So, suppose A is a product of elementary matrices, A is, this is the product, then what is the inverse? So, I can multiply, okay, both will be equal to identity, okay, because if this is A, I multiply on the left by E n inverse, this E n will be gone, I bring E n minus 1 inverse on the left side, what will be left is identity. So, that is equal to this, and similarly the other one, okay, on the left side or right side you can go on bringing inverse one by one, because they are all invertible matrices. So, that says if A is product of these elementary matrices, then what is its inverse? It is precisely this matrix, you can see that, right. Not only it tells you what it is invertible, it even tells you what is the inverse, provided you can write the elementary matrix as you can write the matrix A as a product of elementary matrices. So, it gives two things, if A is a product of elementary matrices, then this equation not only tells you that A is invertible, because A into this matrix, you can call this matrix as B, right. So, B into A is same as A into B equal to identity. So, what should be this matrix? That should be the inverse, right. So, that should be the inverse of A. It tells you how to compute the inverse, provided you can write down the matrix as product of elementary matrices, right. So, one way is obvious. Let us look at the other way around. That means, what is the other way around? Conversely, suppose A is invertible, what we want to prove? That A is a product of elementary matrices. What is the definition of invertibility? It says A is invertible if there is a matrix B, so that A into B is equal to B into A equal to identity. So, okay. Now, let us take this matrix A which is given to us and look at its reduced row echelon form. How do you get the reduced row echelon form? By pre-multiplying by some elementary matrices. So, we have denoted this A tilde to be the reduced row echelon form of the matrix A, which is obtained from A by pre-multiplying by some elementary row operations. Okay. So, each A I is a elementary operation. Now, when A B is equal to identity, what does this give you? A B is identity. So, if I multiply by some matrix, I will get the same matrix, right. So, I get this equation that A is, okay, these are the elementary row operations that we have been doing to get A tilde. So, those row operations multiplied by A B is equal to those row product of elementary. Is that okay? By using the fact A into B is identity. Now, let us, so now what we will do is, we will look at the left hand side and the right hand side and look at their row echelon forms. Okay. So, let us look at, there are two possibilities, that the row echelon form of A is not equal to identity, that is one possibility. That will mean what? That means at least the bottom row is equal to 0, right. There are not as many pivots as the order, right. There is one row which should be 0, right. So, bottom row is equal to 0. So, let us reduce both sides to reduced row echelon form. What will happen to the reduced row echelon form of this product? Last row is of this matrix E n E 1, that is A tilde, right, that is equal to 0. So, that will stay as 0, right. If a matrix has got a bottom row 0, in the reduced row echelon form, that 0 row cannot become non-zero suddenly, right, because non-zero rows has to be at the top. So, we will have the last row as 0, because last row was 0 in this left side. Is that okay? This product E n E 2 E 1 into A B, the first this part of the matrix, that is A tilde, that has a 0 row, when I reduce this product, that will stay as 0 row. Now look at the right hand side, En, E2, E1, that is the right hand side of the same thing. What will be the reduced row echelon form of that? Can it have a 0 row? Can that have a 0 row or not? It cannot. Why? What is the reason? Because if this is the matrix En, E2, the product, I want to reduce it to row echelon form. So I multiply on the left by En inverse. En is invertible, right? I can En inverse, En minus inverse, E1 inverse. What I will get? I will get the identity matrix, and that should be reduced row echelon form. I am only multiplied on the left. So the reduced row echelon form of the right hand side is identity. On the left hand side, bottom row is 0. So you get a contradiction. That means this cannot happen. The reduced row echelon form of A cannot be not equal to. So that means it is equal to identity matrix. That means what? Okay. So if A tilde is, then implying what is A equal to then? If the reduced row echelon form of matrix is identity, that means what? A pre multiplied by E1, E2, En is equal to identity, right? And what is A equal to then? That is a on the right, take it on the right hand side. So A must be equal to E1 inverse, E2 inverse, En inverse. Clear? But if E1, E2, En are elementary, their inverses are also elementary matrices. So here is a fact which we should have observed earlier. If you take an elementary matrix which is invertible, for example, interchange I with J, what is the inverse? J with I, that is again an elementary matrix, again the same, right? Row operation only. So all these are invertible matrices, they are all elementary matrices. So A is a product of elementary matrices. So we have proved a theorem, so namely that if A square matrix n cross n is invertible if and only if it is a product of elementary matrices. So this gives us a method of not only saying something, actually proving also. Okay. So let us go ahead and look at some more examples. So we are going to look at, so we proved that A is invertible if and only if A is a product of invertible matrices, right. So let us start with some matrix. So let us start with some matrix A which is n cross n. So what we want to do, we want to check is A invertible, is A invertible, that is one question we want to answer. And second, if yes, how to find its inverse, right. So given a matrix A, we want to check whether it is invertible or not, right, and whether we can find out the inverse of that or not. So what should be the strategy? It says A is invertible if and only if it is a product of invertible matrices, right, and in that case its row echelon form we saw should be equal to identity, right. In that case the row echelon form of A should be equal to identity matrix. So the idea should be take the matrix A and find its reduced row echelon form. If that is identity, it will be invertible, that is one, right. Now I also want to compute A inverse, right. So how will I compute A inverse? We just said that if you take a matrix A, right, if so if A is the matrix right, and A tilde is E n minus 1, E2 and E1. So, let I am just revising again what we proved in the theorem. If this is so, right, is the reduced row echelon form of A, that should be equal to identity, right, that should be equal to identity. So, if that is of A, okay, then what should happen? A is invertible, that we have already said, and right, this is identity. So, what is A inverse equal to then? We just now saw A inverse is equal to inverses of these multiplied together, right. That means, how do I get that? So, I want E n inverse. So, let us apply that. See, if I apply the operations again, I will get back the A, right. So, this if I want to take it to the other side, I will multiply it by E n inverse, right. That means, what I should be doing, I should be keeping A and identity on side by side, go on doing operations, row operations on, go on doing row operations on A, same row operations you keep on doing on identity matrix, right. So, this will change, A will change to identity and this will change to some matrix B, then B is the inverse of A, that is what it tells us, right, clear. So, let us try to do one example of this. So, let us take the matrix A, I am just writing randomly some example 1 2 3 minus 1 0 1 1 0 2. Let us write this matrix. Okay. It has to be a square matrix if I want to analyze its whether it is invertible or not. So, it is 3 cross 3, this is a matrix which is 3 cross 3. I want to check whether it is invertible or not and can I find its inverse, right. So, what we do is, because the same operations I would like to do it on identity also. So, we write a new matrix which is A along with identity. So, we write 1 2 3 minus 1 0 1 1 0 2 and what is the identity matrix of the same order 1 0 0 0 1 0 0 0 1, right. So, that is this matrix. What is my aim? Look at the part which is in A, okay. Look at the part which is in A. So, this is the part which is in A, okay. On that I should do row operations and reduce it to reduce row echelon form, but same operation I should be keep doing on identity also on the bigger matrix also. So, that I keep track of what is happening. So, let us do that. So, this is equivalent to, let us do those operations. Okay. So, 1 2 and 3 1 2 and 3 1 0 0, anything required in the first row, first entry itself is 1, pivot is 1. So, we are happy. So, below that everything should be 0. So, I should add R1 to R2. So, this will become 0, this will become 2 and this will become 4, right. So, add, so this will become 1, this will be 0, this will be 0. Oh, that is 1, right. So, we should change it to that is 1 and that is 0. Last one as it is, for we have not done anything till now. I want to make the last one also 0. So, what I can do, either I can add these two R2 and R3 or minus R1 with R3, I can add that whichever I like. So, let us add, because minus is already there. So, R2 added to R3. So, this will be 0, right, this will be 0, this will be 3, okay. Add, so this is 0, this is R2 to R3 0, no sorry. So, add 0 1 and 1, is okay. Now, what should be the next step? I have gotten the first pivot in column 1, everything below that 0. Go to the next column now. I should be looking at that part of the matrix, right. I should be looking at only which part of the matrix now? Only this part of the matrix, right. Non-zero entry is 2. I should make that entry as 1. Okay. So, let us do that. So, this is equivalent to 1, 2, 3, 1, 0, 0. This is 0. To make this 1, what should I do? Divide this row by 2. So, 1, 2, 1 by 2, 1 by 2, 0, okay. And the last one is 0, 0, 3, 0, 1, 1, right. So, I have got a pivot in the second row at 1. Next step, I should make everything in that column to be equal to 0. So, let us make that. So, that is equivalent to 1, 2, 3, 1, 0, 0. Okay. So, what shall I be doing? Multiply the second row by minus 2 and add it to the first row. So, that will become 0 if I do that, remove everything. So, multiply and add, this becomes 0, multiply this with minus 2 and add, that becomes minus 1, multiply by this with minus 2 and add. So, that becomes, is it okay? Minus 2 and add, minus 2 and add. So, minus 1 and 0, is that okay? Right. So, second one 1, 2, half, half, 0 remains as it is, and the third one 0, 0, 3, 0, 1 and 1, right. So, I have achieved the second pivot which was coming in column 2 made 1, everything else in that column as 0. I should be writing on the side actually, right, those operations to keep track what I am doing. Okay. So, when you do it, you should write that, so that you can track back what is happening. So, let us write now equivalent to, what should be my next step? I should be looking at this part of the matrix, right. Up to here I have column 2, I have done it. So, for that only 3 is there, which is non-zero entry. So, that is a pivot. I should make that pivot equal to 1. So, 1, 0, minus 1, 0, minus 1, 0, and 0, 1, 2, half, half, 0. So, that is 0, 0. What should be doing? Dividing this last row by non-zero scalar, that is 3. So, 1, 0, 1 by 3, 1 by 3. So, that will be my form here. Still I am not complete, because pivot is 1 in the last column, everything else should be made as 0. So, what shall I do? Add it to the first one. So, 1, 0, 0. When I add, so this is 0. So, minus 1 plus 1 by 3 and 1 by 3. So, that is 0, 1. Okay. I want to make this also, let us do simultaneously now. So, this 2 also I want to make it 0. So, I should multiply R 3 with minus 2 and add. So, okay, minus 2 and add. So, this will not change. So, 1 by 2 minus 2 by 3, this part, and that will be minus 2 by 3. So, okay. The last row is 0, 0, 1, 0, 1 by 3, 1 by 3. So, what is my reduced row echelon form of the given matrix? That is identity, right. So, that means the matrix is invertible, and that should be the inverse of the matrix. So, we can write from here A. So, implies A invertible, and A inverse is equal to 0, minus 3, so minus 2 by 3, 1 by 3, half, that gives you 6, 3 minus 4, 2 by 6. anyway does not matter, simplify 1 by 3 1 by 3, right. So, this part, so we are just saying that this part is precisely the inverse, right. So, this method, so this theorem which we proved that A is invertible if and only if it is a product of elementary matrices, that not only tells us to check whether a matrix is invertible or not, at the same time it gives us a algorithm for finding the inverse also, right, checks and finds both, right. So, what you do, take the matrix A, along with it write identity matrix of the same order, right. So, you will get a bigger matrix whose number of rows will be same, but number of columns will be doubled, right. Now, go on doing elementary row operations on the A part of the matrix. Idea should be to reduce it to reduced row echelon form, but do the same on the bigger matrix itself, right, not only on part A, on the part of identity also. So, that will transform identity matrix into something. If your transformed matrix, the reduced row echelon form of A is identity, then in the last step you can say that that is invertible. If it is not, then A is not invertible, right. If it is identity, then the transformed matrix identity which has changed to, that will be the inverse of the matrix, right. So, this helps us writing elementary row operations as matrix multiplications, gives us a benefit that we can put it on a computer and ask the computer to check whether it is invertible or not and find the inverse for me, right. Everything is in a matrix multiplication, whatever elementary row operations I am doing, you can writing on the matrix multiplication, and eventually identity matrix which is changed to something will give me the inverse of the matrix. So, checking and finding both at the same time, right.